In this Q&A video, we're going to be answering the question, why do you interconnect and divide by 4 when you're testing a ring final circuit? This video relates to the just brilliant ring final circuit adapter from Motrel. This is a product that I wish had been around for decades because it just makes life so much easier when you're testing. I've made a full demo video on this, so please do go and check that out after watching this video. It's awesome. The product, that is, not the video. The video is just me being average and nerdy. Now, there's been quite a bit of debate recently on social media about ring final circuits and how relevant they are to modern electrical installations. But whether you think they're an enduring testament to ingenuity or an outdated nightmare, the fact is that even if they were outlawed tomorrow, they'd still be a big part of our lives in existing installations. So it's important to understand the processes involved when we test them. So of course we know that the first thing we do is we test for continuity between the two line conductors, giving us our so-called little r1 value. Then we do the same for the two neutral conductors and the two circuit protective conductors, and that gives us the little rn and the little r2 values respectively, and we record those results on the test sheet. Now, the purpose of this part of the test is pretty clear. We're just trying to confirm that the individual conductors go out of the consumer unit and come back again, giving us a true ring circuit. However, this test in itself is not enough to prove that the ring circuit is compliant. For example, if someone got a bit confused during the installation of a new ring, or if an existing ring had been added to by amateurs over the years, we could end up in a position where the circuit has been wired incorrectly with a smaller loop than was previously thought, and a long leg going off with spurs off spurs. Now, this is obviously a problem if left, because those sockets that were spurs off spurs are being protected by a 32 amp MCB, and the cable feeding them can only really handle 26 amps at the very most. So how can we tell after installation that this hasn't happened? Well, that's where the interconnection comes in. I've got here a representation of a ring circuit with the line, neutral and CPCs shown going out to each socket and then back to the consumer unit. Each little mark of tape on the conductors is where it enters a socket, so they represent the socket outlets. Now, what we normally do is at the consumer unit, we normally take the neutral from one leg of the ring and connect it to the line conductor on the other leg. So here you can see we've got the neutral from one leg of the ring, and we're going to connect that onto the line conductor from the other leg of the ring, as you can see here. And then we do exactly the same but vice versa. So we connect the neutral from the other leg onto the line of the first leg. So we get those connected to each other like so. Then we figure out what value we expect to get at each socket when we test between the line and neutral. And we do that by adding the values of resistance that we measured for the line and neutral together and dividing that value by 4. Why do we divide by 4? Well, that will become clear in just a minute. Now we go to each socket outlet on the circuit and test between line and neutral. If the circuit has been wired correctly, it doesn't matter which socket we go to, we should get roughly the same value every time. Why is that? Well, let's say we go to this socket here as represented by the blue tape. If we pick this up off here and imagine that we're testing between the line and neutral conductors of this ring, so I'll just remove that from there. So imagine that my fingers are the probes. What happens is that when we test across there, you can see we're actually testing across exactly one half of the ring circuit. We're testing from one side of a circular loop of conductor exactly to the other side. So we'll pop that back and then we'll pick up another socket and do the same thing. So again, we can do the same thing. We can test from any point on this ring final circuit. So let's test at the green socket outlet this time, the green and yellow one. And again, if we remove that from the board, you'll soon see that, again, imagining that my fingers are the test probes that we're going to be doing the measuring with, you can see that when we open this out, we very simply test across one big loop of the ring from one side to the other. And it doesn't matter where we test, we should get the same reading every single time. If we get a high reading, then it's possibly an indication that our measurement includes an extra length of conductor, such as you may find if you've got a spur off the ring final circuit. And if you get a series of rising values, then it's possible you've got a spur, off a spur, off a spur, and so on. So that's the reason we do the interconnection before testing at the sockets. It's because it allows you to check that a circuit that you can't see the root of has been wired correctly. But why do we need to do that divide by 4 bit to get your expected value? Well, let's look at the maths involved. we're connected across the two opposite sides of this loop of conductor as we demonstrated a moment ago, which means that we're measuring the resistance of this conductor here and this conductor here. Each section of this conductor is half of the big loop, and the resistance of the big loop is the combined value of the line conductor and the neutral. So the resistance of this conductor is half the combined resistance of the line and neutral. So to find that, we divide little r1 and little rn added together by 2. Then we need to bear in mind that we're effectively measuring the value of two resistors of equal value connected in parallel. So what's the total resistance? Well, do you remember the trick that your college lecturer tried to hammer into your brain just before your Science and Principles exam? Half the value of one of the resistors. So we've divided the resistance of this big loop by 2 to find the resistance of one side of the loop, and then we've halved it again to account for two resistances of equal value in parallel. And when you divide a number by 2 and then divide it by 2 again, it's exactly the same as dividing by 4. Clever stuff. So there we go. That's why we interconnect and divide by 4 when we're carrying out ring final circuit testing. But of course, we want to hear from you. What are your opinions on ring final circuits and the extra testing that they require? Do you think that they've got their place, or do you think they're destined for the museum? Please leave your thoughts and questions in the comments section below, and as always, thank you very much for watching.